Okay, here's an example of projectile motion, but now we have it launched at an angle. So just something to have handy, your formula sheet that you printed at the beginning of the year. All those formulas that we've used for motion, we can use here as well. So having that handy is a good idea. Okay, the ball is launched at 4.5 meters per second at 66 degrees above the horizontal. So let's draw a bit of a picture of what that would look like. So we have our X and our Y. And this Canton's really good at drawing. And we have an initial velocity at 66. That's our initial velocity. So you can imagine that ball is going to come here, it's going to go up, and then it's going to come down. It's because it starts and lands at the same distance from the ground. So you can imagine it has some sort of trajectory like that. What we want to know, this should be a word above, what's the maximum height? So this height above launch level, and how long did it take? Okay. So a couple things we know right away. We know initially the displacement in the y direction is 0 and also in the x direction. We're going to start from 0 right here. We know that the initial speed, initial velocity rather, is 4.5 meters per second. We don't know in terms of x or y how much is in x, how much is in y. So we're going to have to use the vector component method there. Okay, we know that the angle is 66 degrees. And we know the acceleration in the y direction. We know that that is going to be negative 9.81 meters per second. Meters per second squared, that's from gravity. There's no acceleration in the x direction, right? It's going to accelerate in the x direction, or sorry, it's going to be a constant velocity in the x direction. There's going to be acceleration here. So it's going to, first of all, go fast, slow down, stop, and then speed up as it comes down. So that stopping is something that we know. We know the velocity in the y direction at the maximum height is 0. Okay, that is something that we know. Why do we know that? We kind of looked at it. Where did we look at it? Let's see if I have it here. Oh, I got out of it. We learned about that in this section right here. On the course right here, forces in motion. We learned about that when we learned about gravity. This is good because I need to have this here. We learned at its highest point that we have an instantaneous velocity of 0. Okay. And that, what we don't know, unknown, what we're trying to find out, we don't know the y position at the maximum height. We don't know that. And we also don't know time. That's what we want to know, maximum height and flight time. Okay, first thing we need to do is we need to break up. Break up our v initial into vx and vy. Okay, so we have this beautiful initial speed of 4.5 meters per second, and we know that that happens at 66 degrees. Initially, that is how this ball is launched. So in order to get this resultant vector, I know that I must have a vector in this direction added to a vector in that direction to create my resultant. So I know I have a vector in the x direction and a vector in the y direction. Okay, so a couple of things to think about. If I want to know this direction here, this is a 90-degree triangle, I'm going to use SOHCAHTOA. Okay, So if I wanted to know the x, this is adjacent and hypotenuse, I'm going to use cos. So my cosine of 66 is equal to the adjacent over my hypotenuse, 4.5 meters per second. Okay, so my Vx is equal to 4.5 times the cos of 66. That is how I could get that component. I actually won't need my Vx just yet. So I'm going to look at my Vy. If I wanted to know Vy, look, this is directly opposite, and we have hypotenuse, so I'm going to use sine. Sine of 66 equals Vy over 4.5. So Vy equals 4.5, that was meters per second, times the sine of 66. Okay, solving that, we would get 4.1 meters per second. Okay. This is my initial speed, right? This was my initial speed, so my initial speed in the y direction. Now, we have to use some of the information we've learned before. When the ball first leaves your hand, it's going its very fastest. Comes up, goes down, here, back to the original height it started from, all of the potentials back to kinetic, so it's moving just as much negative as it was when you originally threw it up. So initially, if we're going at 4.1 meters per second up, when it comes back down, it's going to be negative 4.1 meters per second squared. So my Vy final, using that principle, is going to be negative 4.1 meters per second. Okay, so this is something that we needed to know. Okay. So let's look what we have here. We have a final velocity in the y direction. What else do we have? We have a initial velocity in the y direction. Final, initial. We have an acceleration in the y direction. And I think we have just about everything we need. Okay, so some of the formulas. Look at this one right here. V final squared equals V initial plus 2 times acceleration gives us our displacement. Acceleration, initial, and final we already have. We can solve for displacement. And that's what the question had asked. It had said, for displacement, it had said, what is the maximum height? That's what we wanted to know. So displacement. Wait a second. At that maximum height, my final velocity is 0. That's what I need to use here. 0 right here. I have my initial in the y direction, my final, and I have my acceleration is negative 9.8. Those are the pieces of data I'm going to use. Okay, so just to recap. My formula, V final squared equals V initial squared plus 2 times acceleration times displacement. I'm only using things in the y direction, okay? So my V final, I'm doing this at the max, my V max in the y direction, my Vy max squared equals my initial, Vy initial squared plus 2 times my acceleration in the y direction times my displacement. I can just write displacement instead of changing. I know this, and I know this, so I can solve for d. Okay, getting d by itself, I'm going to go Vy max squared. I'm going to subtract Vy initial squared, and I'm going to get that to be 2 acceleration in the y direction times displacement. I want displacement by itself, so I'm going to divide by 2 times the acceleration. Okay, that crosses out. I'm just left with displacement. So now I need to put in those values that I know. Okay, I have 0 squared, 0 meters per second all squared, minus my initial velocity in the y direction. We calculated that to be 4.1 meters per second, so minus 4.1 meters per second all squared equals, divided by 2. My acceleration is negative 9.81 meters per second squared, the acceleration due to gravity, and this is equal to my displacement. Okay. Calculating this out, my units, I'm going to have meters squared per second squared divided by, let's look at my units here, meters squared per second squared. I'm dividing by meters per second squared. When I divide by a fraction, it's really multiplying by the reciprocal. Okay, so my second squared cancel out. I have meters squared divided by meters. I'm going to be left just with meters. Okay, so my unit is meters. Sorry, my regular program wasn't working, so I'm using this new program, which I don't like as much. So my displacement is in meters. I'm going to take out my calculator. I'm going to go 4.1 squared negative divided by 2 times negative 9.8. I'm going to have a negative divided by negative. I'm going to come out with a positive displacement, which makes sense. I am throwing the ball up. When I actually go through and use significant figures, I got 0.68. 86 rather. I can't use an eraser on this program, and I'm not sure why, but we will make do until my computer gets fixed. 0.86 meters is my displacement. Second part of the question said, okay, solve for the time. So I need to go shopping for a formula that has time in it. And the formula that I see right away is right here. V final equals V initial plus acceleration times time. So let's use that. V final equals V initial plus acceleration times time. Okay, so getting time by itself, I'm going to go V final minus V initial equals acceleration times time. I'm going to divide both sides by acceleration. So V final minus V initial, I divide by acceleration. Okay. So what do we have a V final? Yes, we said by symmetry that this was going to be, we're still looking at the y direction. V final in the y direction, V initial in the y direction, and A in the y direction. Is negative 4.1 meters per second. Initially, we had 4.1 meters per second. That's what we found up here. We found our V. Where are we at? V initial was 4.1. V final was negative 4.1. Okay. And our acceleration in our y direction, of course, is negative 9.81. That is a known. That is something we will always be given. In fact, it's on your formula sheet, and that is found. Sorry, that acceleration due to gravity is right here, 9.80. Oops, 9.80 we should have used. Meters per second squared. So that should always be given to you. Okay, let's look at our units. Meters per second divided by meters per second squared. That's going to give us in seconds. Minus 4, that'd be negative 8.2 divided by negative 9.8. Once I do that in my calculator, significant digits, I should get 0.84 seconds. Okay, there's another example that I've posted as well. They're going to use a lot more subscripts than we're used to, but it still follows the same patterns. There's 3 questions I have you try as well with the answers. Do email me if you have any questions or you need some help.